In the third, last learning sequence of block number 2, we will discuss how to compare samples coming from different populations and closely related problem, how to estimate effects. So let me start with some intuition again and probably some defining a problem actually. So far, when we discussed different statistical methods for descriptive or inferential statistics, we considered one single sample coming from one single population. And then this population has various parameters. For example, if we talk about normally distributed characteristics of this population, for example, sugar content in apples, or maybe a height of people or anything like this, we have some parameters which define how this particular characteristic varies in the population, right? For example, in case of normal distribution, we have two parameters, mu and sigma. In this learning sequence, we will talk about several populations, about several samples coming from different populations. Imagine that instead of one single apple tree, or one single apple garden, we're talking about 3 different apple gardens belonging, for example, to 3 different people. So imagine that these 3 persons have own gardens, apple gardens. They actually have the same varieties of apples, but they would like to find out whose apples are actually the sweetest. Everyone takes care of the apples in its own way, and therefore everyone thinks that, okay, my garden produces the best or the sweetest apple trees. And then your task will be to find this out if there is any difference among the 3 gardens by taking samples from every garden. So in this case, you have not just one, but 3 populations. So you have population, let's call it John's population, John's apple garden. This is average and standard deviation of the sugar content in this garden. Then we have, for example, Jill. This is average and standard deviation of sugar content for apples coming from Jill's garden. And then, for example, we have Bill, and these are parameters of sugar content distribution in Bill's garden. And the task is to compare these parameters, to compare, for example, average sugar content by taking a sample. So we never know the true parameters. We take 3 samples from 3 different populations, and we'd like to find out how likely these populations are similar or different. Okay. Being more scientific, you can think about the following situation. Again, we have 2 gardens, so maybe 2 parts or 2 randomly splitted trees in one single garden. And then we have, for example, 2 fertilizers. So we have fertilizer A, we have fertilizer B, and we would like to find out if there is any difference between the fertilizers, or in this particular case, which fertilizer gives us the sweetest apples, right? So we would like to see if there is an effect from changing fertilizer to the sugar content in apples. In this case, we estimate an effect from fertilizer. And then you can think about more complicated situation. For example, in this particular case, I have chemical reaction, and I have 2 parameters which I would like to change, to optimize. It's the temperature of reaction and the pressure inside the reactor. You can see that I tried 2 different temperatures, 120 and 140 degrees, and 2 different pressure values, 20 and 40 bars. And then you can see I tried all possible combinations. Why it's important to try all possible combinations, we will discuss it also in this learning sequence. But so far, I tried all possible combinations, right? In this case, population will be like when you run this reaction with these particular fixed parameters infinite amount of times, or at least very large amount of times. And then in this case, we have 4 populations, right? So if you run every case many times, billion of times, and then compute average and standard deviation of outcome, for example, reaction yield, then you will get parameters of 4 different populations. And in this case, you have like several tasks, like to find out if temperature has an influence on average yield, to find out if pressure has an influence on average yield, and also to find out if there is any interaction, for example, right? So all these things can be solved by the methods that we are going to discuss in this particular learning sequence. Let's say we have 2 populations, like 2 gardens, right? Here we use fertilizer A, here we use fertilizer B. So these are parameters on the first population. In this case, when I say parameter, I mean parameters of particular characteristic of this population, for example, sugar content, right? And this is parameters of distribution of the sugar content in the second population when you use fertilizer B. So to find out if there is any difference between these 2 fertilizers, to find out if switching from one fertilizer to another fertilizer gives any systematic effect on average sugar content, you need to take a sample. So you need to take a sample from the first population, you need to take a sample from the second population and then do something with the samples and then make an inference, right? So to find out if we can say something based on our samples about the populations, right? So for example, populations are possibly different or populations are possibly similar. We can actually generalize it. You can think about this procedure, estimating effects, as a part of any experimental work. So every time you do an experiment, you in fact run a test or serial tests. The aim of this test is to find out how input variables of a process or a system influence the output variable, right? So this is a general scheme. You have a system or a process. It can be apple garden. It can be, for example, cooking. It can be chemical reaction. It can be running a marathon. It can be anything. And then you have several inputs, which you can change directly, manually. And then you have an output, which is like a quality parameter of this system. And the overall idea of the methods that we are going to talk about in this learning sequence is to find out how input can influence the output. And if there is an influence, there is a systematic influence. For example, in case of fertilizer example, your system, it's apple tree or several trees if you have a garden. Your input, it's a fertilizer, so you have two different fertilizer. And your output, it's a sugar content in the apples taken from these trees, right? Now let me recall a couple of specific definitions, right? So I will use a simplified system, not the apple trees, not the chemical reactions, but for example, making a popcorn. So when you make a popcorn, you have some corns, you put these corns to microwave oven, you set power, you set time of the microwave oven, and then at the end, you have the popped corns, right? So the popcorn. So in this case, you have several things which can potentially influence the result of this cooking. Let's call it cooking, right? So first of all, you have some conditions which you can change, and they possibly can indeed influence the quality of the popcorn. For example, time, power, and then how much of salt you add, right? Then you can also have some conditions which potentially can influence, but for example, you don't want to change them. For example, popcorn brand, you use the same brand, the brand of microwave oven, and then, for example, operator skills, right? Then finally, you have the outcome. That's the popcorn. And you can measure different characteristics of your popcorn. For example, you can measure taste, not measure, but assess taste. For example, you have 3-4 friends who assess a taste between 0 and 10, and then you calculate the average taste, right? And then you also can, for example, assess colors. You can also assess amount of popped corns, how much of popped corns in percent actually you have, and so on. So you can see that these are inputs, and this is the output, right? The inputs we will call factors. So factor, you know that this is a Latin word meaning who which acts. It's something that can change the result of your experiment. And then if you change the factors manually, they are controllable factors. If you cannot control them, they are external factors. For example, let's say the temperature outside or humidity in the room that you're cooking, it's uncontrollable factors because in this particular case, you cannot change them directly. And then when you change a factor, you will always see a change of outcome, even if it's random change. And this change in outcome, change in response, we will call the outcome variable response, is called an effect. So effect, it's a change in response that is caused by changing the factor. For example, in this case, I take one single factor, time. I have time at 120 seconds, I have time at 240 seconds. And then the other conditions are fixed. I didn't change the power, I didn't change anything else. And then I found out that, for example, if I use 120 seconds, I got 31.5% of corns that are popped. But if I use a longer time, then I got it almost 50%. So the effect, it's a difference between these two outcomes. So in this case, I have an increase of by 15% larger corns popped if I use a longer time, right? So in this case, I can make a main effect plot. So effect from time, I can show it as this is the outcome I got when I use 120 seconds. This is the outcome I got when I used 240 seconds. And this is the difference. So the difference between these two outcomes, it's an effect. However, of course, every time I repeat this experiment, and even if I don't change anything, for example, if I keep time equal to 120, this percent of popped corns will be different. So it will vary because we have a lot of also random factors, right? So therefore, we need to repeat experiment with every particular level of factor several times and calculate average instead of taking just one single value. So in this case, you can see that I ran my experiment 8 times. 4 times I ran it with low time, so 120 seconds, and then you can see that indeed the values are slightly different, right? So this is how it looks like. So this is all my values that I got when I ran the experiment with 120 seconds. And then you can think that this is a sample one. This is a sample one which came from a population one. This curve, this is the population distribution, right? So this curve, it shows you the distribution of amount of popped corns if you run this experiment infinite amount of time. So this is the population. And the points are the observed values. This is the sample. So in this case, I have a sample of size 4 taken from this population. Likewise, I have also 4 values which I got by running this experiment 4 times with time equal to 240 seconds. So I changed the factor, right? In this case, I also got 4 different outcomes. The outcomes vary, the percent of popped corns varies. And the same idea, right? So if I repeat this infinite amount of times, I would get a distribution like this. So this is my population. But I got a sample, which is a random sample taken from this population. And in my case, this sample represents the population. So I have 2 samples from 2 different populations, and my task is to compare these 2 samples and say something about 2 populations they came from. Okay. Now, if we assume that, for example, population values are normally distributed, of course, in this case, I cannot treat all 8 values as normally distributed because I have 2 different populations, so I have to treat them separately, right? So if we assume that indeed populations, the percent of popped corns in each population is normally distributed, then I can say that, okay, so the first population has parameters mu1 and sigma1. It's the average and the standard deviation of the percent of popped corns when I run the experiment with 120 seconds, infinite amount of times. The second population has its own parameters, mu2 and sigma2, right? And then look, because I didn't change any external factors, I changed only time, I didn't change any external factors. In this case, it would be reasonable to assume that the standard deviations are the same. So the standard deviations in these populations are the same. So it leads us to a simplified task. We need to compare the average values. And now we can define the effect more precisely. So the effect, actually, we will distinguish between observed effect and theoretical effect. So the observed effect, it's a difference of average outcomes that we observe in particular case. So we have average outcome we got when we ran the experiments using factor at 1 level. Average outcome we got when we ran the experiment using the same factor but at the second level, for example, 2 different times. And the difference between these 2 average values, it's our observed effect. And then the theoretical effect, it's the expected difference. So it's a difference between the population parameters, population average values, which we never know. So the task is now simplified, right? So we would like to assess a difference of population means by knowing a difference of sample means. Well, how to do it? Well, we already know from the previous learning sequence how to do it individually for every population, right? So if you take only population 1 and only sample 1, then we know that average of sample is normally distributed around average of population. We can use t-distribution instead of normal distribution if we don't know the standard deviation of the population, so it's approximation, right? And then in this case, we can use t-distribution, and then this is the idea, right? So m, this value t s over square root of n, it's the error margin. It's how far sample average can go from population average for this particular sample size, right? And then we know that t-distribution looks like this. It depends on degrees of freedom. The more values you have in your sample, the closer t-distribution will be to the normal distribution. And then the less values you have in your sample, the more kind of, the bigger uncertainty you will have compared to the normal distribution. But the idea is that you can always get this t-value and you can always compute confidence interval or make, for example, a t-test, right? So, okay, so let's take our case. So in our case, we have every sample is a size of 4, so we have 4 outcomes. And for 95% of the values, the t-score will go from minus 3.18 to plus 3.18. How you can find it, you remember that because you have 95% here, so you have 0.025 here, I should use not percentage, but just a ratio of 1. And here you also have 0.025. So if you run, for example, Qt for 0.025 and 3 degrees of freedom, because it's 4 minus 1 in this case, right? You will get this value, minus 3.18. Okay. Now, if we know this value, then we know that the error margin will be by 3.18 standard errors. And that's the possible largest difference between average of your sample and average of your population in 95% of the cases, right? Now we can use it to make the calculations, right? So this is my sample 1. So I will use R. So first of all, I make a vector with all these 4 values that I got from here. Then I compute average, 32.6 if you round it to 1 decimal. Then I compute standard deviation, 2.3. Now I can compute the standard error. Why it's 2? Remember that it's a standard error, it's s over square root of n, and n is equal to 4, so it will be s over square root of 4, or half of s, right? And this is my t value that I calculated before. So this is my error margin for 95% confidence. And now I can compute the confidence interval for the average percent of popped currency if I run it with 120, right? So this is it. So I know that I don't know the real mu value, but with 95% confidence, it will be somewhere in between. Likewise, I can do it for the second population, for the second sample. So first of all, I collect all these values into a vector. Then I compute mean, I compute standard deviation, I compute error margin. Again, it's standard error times t. Now I got these values for the second population. And now I can also define my main effect as simply like a 2 confidence intervals, right? So this is confidence interval for mu1, this is confidence interval for mu2, and then you can see these intervals at least not overlapping. So it means that we quite likely have a systematic effect. But again, in this case, I know the variation, the uncertainty for individual means, but I don't know the uncertainty for the effect. So how to find how big the effect is, the real effect, how big the uncertainty for the real effect is, and so on and so forth. So it means that we need to modify this procedure in order to be able to operate with difference of mean values. And that's exactly what we are going to talk about in the next video.